So let us continue with the proof of the Bonnet's mean value theorem for integral calculus. We have this Riemann sum R of fg pi equal to summation j from 1 to n f of cj, g of cj, tj minus tj minus 1. This Riemann sum will approximate the integral from a to b ft gt dt. Now, we will apply the method of summation by parts to this Riemann sum, but first we must explain how to choose a Cj. As explained in the last lecture, the Cj is chosen to be that point in the intervals tj minus 1 tj such that integral from tj minus 1 to tj gu du equal to g of cj into tj minus 1. So, this is the setup. Now, we will apply the rule for summation by parts. So, on this. So, R fg pi equal to summation j from 1 to n f of cj integral tj minus 1 to tj gu du. This integral we will write it as a difference of two integrals, integral from a to tj fu gu du minus integral from a to tj minus 1 gu du. So, now we have got this summation aj bj minus bj minus 1. So, now we are ready to apply the rule for summation by parts. So, it has become minus summation j from 1 to n f of cj minus 1 integral from a to tj minus 1 gu du plus the last term in the summation by parts, that a and b n term, f of cn integral a to tn gu du. Now, as the mesh of the partition goes to 0, what happens? The Tn is basically b and the last displayed term goes to f of b minus integral a to b gu du. Remember that Cn is a point in the last piece in the Riemann sum, Tn minus 1 to Tn. What is Tn? Tn is b. And as the mesh of the partition goes to 0, Cn approaches b. And when Cn approaches b, f of Cn approaches f of b minus. Here the monotonicity is being used. And now we deal with the first term in red, which is j equal to minus summation j from 1 to n f of cj minus f of cj minus 1 integral a to tj minus 1 fu du. Integral a to tj minus 1 gu du. So, let us look at this function phi of x, which is integral from a to x gu du. This is a continuous function with respect to x, and let little m and capital M be the supremum and infimum of phi. Then what happens? Little m less than or equal to integral a to tj phi u du less than or equal to capital M, and multiply by f of cj minus f of cj minus 1. Here again we are using the monotonicity. If you multiply, it should not happen that for certain terms the sign changes this way and for the certain terms the sign changes that way. That should not happen. Here we are crucially using the monotonicity of f. So, we multiply by f of cj minus f of cj minus 1 and we keep adding. We get m times f of cn minus f of c1 less than or equal to j. What is j? J is this piece that is in red, and less than or equal to capital M times f of Cn minus f of C1. Again, let the partitions become finer and finer and the mesh of the partition goes to 0. Then what happens when the mesh of the partition goes to 0? Little m times f of b minus f of a plus. C1 will converge to a and Cn converges to b. So, the corresponding values of f will go to f of b minus and f of a plus. So, little m times f of b minus f of a plus less than or equal to limit of j, the red term that I displayed, less than or equal to m times f of b minus f of a plus. Now, let us divide by f of b minus f of a plus, and we see that limit of j by f of b minus f of a plus lies between little m and capital M. So, by continuity of phi, there is a c between a and b, the intermediate value theorem, such that limit of j equal to f of b minus f of a plus times integral a to c gu du. So in the limit, what do we get? In the limit we get integral a to b f of t g of t dt equal the red terms go to minus of f of b minus f of a plus integral a to c gu du plus the last term f of b minus integral a to b gu du. Now a little simplification will give you the result that was displayed, and that completes the proof of the first part of the Bonet's mean value theorem. Observe and flag all those places where monotonicity of f was used. It's very, very crucial. Now, how to get the second and the third parts of Bonet's theorem? Now, let us look at this equation. Integral a to b ft gt dt equal to f of b minus integral c to b gu du plus f of a plus integral a to c gu du. Let us subtract off a term from both sides. Let us subtract off f of a plus integral a to c gu du. So, in other words, a plus term is gone from the right hand side. From the left hand side, what have I written? I have taken this subtracted term inside the integral a to b f of t minus f of a plus into gt dt. But remember that what I am subtracting off is an integral from a to c, and on the left hand side I have an integral from a to b. So, I have actually subtracted more than I am supposed to. So, I readjust it on the right hand side by subtracting the same thing. So, I get f of b minus f of a plus integral c to b gu du. That is how I get the fb minus f of a plus term. So, now observe that f of x minus f of a plus is monotone decreasing and non-negative, because I have subtracted off the limit at the lowermost end. So, it is going to be non-negative, and we get the second part of Bonet's theorem, because think of f of x minus f of a plus as capital F of t, and that is exactly the second part of Bonet's theorem. The third part of the Bonet's theorem is similar. We will subtract off fb minus integral c to b gu du, but then we will have to assume that f is monotone increasing. So, the proofs are very similar, and I am leaving it to you to do them. And so, the proof of Bonet's mean value theorem is complete. Now, we are finally ready to go to the proof of Dirichlet's theorem. So, we recall right from the first module that the nth partial sum of the Fourier series for f, Sn fx, is given by integral minus pi to pi dnt f of x minus t dt, where dnt is the Dirichlet kernel. Now, the Dirichlet kernel is 2 pi periodic, f is also 2 pi periodic. I am going to extend f as a 2 pi periodic function to the entire real line, of course, and work with it. And so, Sn of f of x will be equal to integral x minus pi to x plus pi dnt f of x minus t dt, because I can take any interval of length 2 pi and they will be equal. The integrals over those will be equal. So, now we must write out the Dirichlet kernel. The Dirichlet kernel consists of two pieces, cos nt, an isolated cos nt term, but cos nt into f of x minus t dt, that will go to 0 by Riemann-Lebesgue lemma. There will be a sin nt into cot t by term, which is a troublesome term, and that has been displayed here. So, 1 upon 2 pi integral x minus pi to x plus pi sin nt cot t by 2 f of x minus t dt. It is this piece that we must worry about, and we must take the limit of this as n tends to infinity. The other piece went to 0 anyway. So, cot t by 2 behaves like 2 upon t. So, add and subtract 2 upon t. So, cot t by 2 is cot t by 2 minus 2 upon t plus 2 upon t. But cot t by 2 minus 2 upon t is a continuous function. It has a limit as t goes to 0, and so define this value at 0 to be this limit, and it becomes continuous. So, in the last integral, if I replace cot t by 2 by cot t by 2 minus 2 by t, then Riemann-Lebesgue lemma applies and it goes to 0. So, what we will be left with? 1 upon 2 pi integral x minus pi to x plus pi sin nt into 2 upon t into f of x minus t dt. The 2 cancels out, you get 1 upon pi. So all we are left with is Sn of f of x. When you want to understand the limit of Sn of f of x, that limit is the same as the limit of the expression 1 upon pi integral x minus pi to x plus pi sin nt by t f of x minus t dt. So that is all that is left over. So now to deal with it, that integral over x minus pi to x plus pi should be broken up into the integral over certain disjoint intervals. So first let us write minus pi to pi as a union of closed interval which are non-overlapping, meaning that I1 is a, say, minus pi to t1, I2 will be t1 to t2, I3 will be t2 to t3. So they are closed intervals which are non-overlapping. Any two consecutive ones will have exactly one endpoint in common. So that interval minus pi to pi has been written as a union of finitely many non-overlapping intervals, and f restricted to each ij is continuous and monotone. Now let us assume that the point at which we are discussing is not in ij. That point is going to be in exactly one or two of these intervals. If it is in the interior of one of these intervals, it will be only in one of them. Or it may be an endpoint and there may be two adjacent intervals. So first assume that x doesn't belong to the closed interval ij, and let us call ij to be c minus d. Which means what? Which means x minus c and x minus d have the same sign. They are both positive or they are both negative. Neither of them is 0. So 1 upon pi x minus ij, x minus pi to x plus pi, that will be x minus I1 union x minus I2 union x minus I3 etc. union x minus Ik. Now I am looking at the contribution of the integral from x minus ij sin nt by t f of x minus t dt. That's plus or minus depending on whether the x minus c and x minus d are both positive or they are both negative. I am clubbing them as by putting a plus minus 1 upon pi integral x minus d to x minus c sin nt by t f of x minus t dt. Now the thing is obvious, we must put nt equal to u, and then we will get sin u by u du f of x minus u upon n. That's exactly what I have done here. I have put nt equal to u, the integral becomes plus minus 1 upon pi integral from n into x minus d to n into x minus c sin u by u f of x minus t upon n dt. Now integral sin u by u is convergent, and x minus c and x minus d are both, say, positive, for example, positive constants. So n times x minus c and n times x minus d are gone far away, and so by Cauchy's criterion this limit must be 0. So this limit is 0. Please think about this if you are not clear about this. Now let us consider the case when x is in one of the intervals IL. So let us call IL to be the closed interval AB. So x minus b and x minus a have opposite signs this time. They don't have the same sign, they have opposite signs, and both cannot be 0 because x can be the left endpoint or the right endpoint. Now we split the integral on x minus IL into a sum of two integrals, one from x minus b to 0 and the other from 0 to x minus a. So just I multiplied the whole thing by pi just to avoid these fractions. Pi times integral over x minus IL turns out to be integral from x minus b to 0 sin nt by t f of x minus t dt plus integral from 0 to x minus a sin nt by t f of x minus t dt. So now let us look at what happens to these integrals. Again I am going to put nt equal to u, and the integrals become integral from n times x minus b to 0 sin u by u into f of x minus u upon n du plus integral 0 to n times x minus a sin u by u f of x minus u upon n du. Now if x minus a or x minus b is 0, then one of these will drop out. If x minus a is 0, then the second one will drop out. If x minus b is 0, the first one will drop out. There is no point in writing those integrals. So now we need to deal with this as limit as n goes to infinity. So we have to use theorem 85. What is theorem 85? We use Bonnet's mean value theorem to derive a corollary, which is going to be used. Remember theorem 85. What does that theorem say? Limit as omega tends to infinity, integral from 0 to s, f of u sine omega u by u du equal to pi by 2 times f of 0 plus. This theorem, which we proved using Bonnet's mean value theorem, is now going to be crucially used. So let's see how to use this theorem. So we get the precise value pi by 2 into f of x minus plus f of x plus. You see, this is exactly what we have over here. Instead of omega, I will exactly have this expression. I will get exactly this arithmetic mean, pi by 2 times f of x minus plus f of x plus. Now, if one of these terms will get omitted, if x minus a or if x minus b is 0, that is if x is an endpoint of a IL. In such a case, there will be a non-zero contribution from two adjacent intervals, and we will get that at a point of discontinuity, the limit of Sn fx will be exactly pi by 2 times f of x minus plus f of x plus. Of course, we have to add up the contributions, but remember that if x doesn't belong to an ij, then that term doesn't contribute. We have seen that right at the beginning. The proof of the Dirichlet's theorem is complete, including all auxiliary propositions. We split the integral into two pieces, one from x minus b to 0 and from 0 to x minus a. So, it is pi times integral over x minus IL equal to integral from x minus b to 0 sin nt by t f of x minus t dt plus integral 0 to x minus a sin nt by t f of x minus t. Now, we have to appeal to the lemma which we proved using the Bonnet's mean value theorem, namely limit as omega tends to infinity, integral 0 to s f of u sin omega u by u du equal to pi by 2 times f of 0 plus. If you use this lemma to each of the two pieces that you see in the first displayed equation on this slide, then you will see that you get precisely the contribution as to 1/2 of f of x plus f of x minus. That is exactly what we have written in this slide. Now, the last part of this is the Gibbs phenomenon. We shall not discuss this Gibbs phenomenon in detail, since an excellent account of it is available on page 207 to 210 of Bachman and Nareki's book that has already been cited. A very detailed account of it with historical development and in a much broader context is also available in the book of Jerry, The Gibbs Phenomenon in Fourier Analysis, Splines and Wavelet Approximations, Kluwer Academic Publishers. For the case of the signum function, 1 on the interval 0 to pi and -1 on the interval 0 to minus pi, we saw that the Fourier series converges to 0, but the function has a jump discontinuity there. It is of interest to know what happens to the partial sums. How do the partial sums behave around the origin? The partial sums overshoot and undershoot the values plus minus 1 by 9%, exactly. The overshoot is 9% and the undershoot is 9%. This is called the Gibbs phenomenon. A detailed analysis cannot be undertaken here because of lack of time. This is the last lecture in the series and we are already running out of time, and so I shall not discuss this in detail. I have given you two references and I urge you to look at these two references. So now, to conclude this lecture series, I have put in the road ahead. What lies ahead? In which directions can we go from here on? So we shall not prove any of the results here, but refer to Gromer's Geometric Applications of Fourier Series and Spherical Harmonics, Cambridge University Press. So one could develop the theory forward in several ways, and we indicate one method that is very important for applications, mainly in engineering applications and optics and other areas, namely the theory of spherical harmonics. To motivate spherical harmonics, let us start with the familiar identities. Cos n theta equal to n choose 0 x to the power n y minus n choose 2 x to the power n minus 2 y squared plus n choose 4 x to the power n minus 4 y to the power 4, etc. Sin n theta is n choose 1 x to the power n minus 1 y minus n choose 3 x to the power n minus 3 y cube plus n choose 5 x to the power n minus 5 y to the power 5 minus, etc., where what are x? X is cos theta and y is sin theta. These are very, very familiar expressions, and we can derive them using the de Moivre's formula. But the two polynomials that you see displayed on the right hand side, they are both harmonic polynomials. They satisfy the Laplace's equation, Laplacian of u equal to 0. To prove that they are harmonic, you simply put z equal to x plus iy. Then what is cos n theta? Cos n theta by de Moivre's theorem is twice real part of z to the power n. Now z to the power n is a holomorphic function, so its real part is harmonic. So what we are looking at is a polynomial which is harmonic, and we are restricting the harmonic polynomial to the unit circle, and that's how we get those expressions. So now what we must look at is the basic building blocks of classical Fourier analysis are homogeneous harmonic polynomials in two variables restricted to the circle x squared plus y squared equal to 1. So how do we generalize this to higher dimensions? The one way to generalize this to higher dimensions is to introduce spherical harmonics. So what are spherical harmonics? You take the unit sphere SD minus 1 in space of d dimensionals, RD. Take the space of d dimensions RD and look at the unit sphere centered at the origin. So the d-dimensional spherical harmonic is a restriction to the sphere of a homogeneous harmonic polynomial in d variables. In other words, you take a homogeneous harmonic polynomial in d variables. Take a polynomial in d variables which is homogeneous and which satisfies the Laplace's equation, which is called a homogeneous harmonic polynomial, and restrict it to the unit sphere SD minus 1, and what you get is called a spherical harmonic. So the idea is to express an L2 function on the sphere as a linear combination of these spherical harmonics converging in L2 norm to the function f. In other words, the spherical harmonics will form a complete orthonormal basis, orthonormal after subjecting it to Gram-Schmidt's process, and we get a basis, we get an L2 basis by this process involving spherical harmonics. Let us introduce some notations. VDG, script VDG denotes a set of all homogeneous polynomials of degree g in d variables, and HDG is a set of all homogeneous harmonic polynomial of degree g in d variables. Clearly, VDG is a vector space and HDG is a vector space. The Laplacian is a mapping, is a linear transformation from VDG to VDG minus 2. When I differentiate a polynomial twice, the degree goes down by 2. So a homogeneous polynomial remains homogeneous when I differentiate it. So the Laplacian is a second order differential operator. So it will take the vector space VDG to the vector space VDG minus 2. This linear transformation turns out to be surjective. The proof is not difficult. You can try it yourself if you wish. So it is a surjective linear transformation. So what is the kernel of this? The kernel of this is exactly HDG. What is the kernel? Kernel is a set of all homogeneous polynomials of degree g in d variables satisfying the Laplace's equation, Laplacian of u equal to 0. In other words, they are harmonic homogeneous polynomials of degree g. In other words, they are elements of HDG. So delta is a surjective linear transformation from VDG to VDG minus 2. The rank nullity theorem will tell you that the dimension of HDG is the dimension of VDG minus the dimension of VDG minus 2. The dimension of VDG is well known. It's an exercise that is displayed in the slide. It is d plus g minus 1 upon g. So we know the dimension of VDG, we know the dimension of VDG minus 2, and so we know the dimension of HDG, the difference of these two numbers. So now we discuss the orthogonality properties of spherical harmonics. If f and g are harmonic homogeneous polynomials of different degrees m and m is less than n, then these harmonic polynomials are orthogonal and they form a basis for L2 of SD minus 1 with respect to the area measure on the sphere. So now with this one can develop a Fourier series, a theory of Fourier analysis for spherical functions, so involving spherical harmonics. And this is a very vast subject, and that's a very important subject. It has lots of applications to engineering and science. It is also related to many other parts of pure mathematics such as representation theory and Lie groups. When you look at the orthogonal groups and you look at the irreducible representations of the orthogonal groups, the spherical harmonics play a very significant role, and this opens up an entirely new chapter in Fourier analysis going beyond what we have studied here, and I'll stop here. Thank you.